a new friend to give our colloquium. So Niccoló Veronesi has been here for some months now and made himself right at home in the department. He attended the University of Bologna and then went to his PhD work at Leiden Observatory in the Netherlands, and now is on a postdoc here with Maria Cerisi. And it's all about black holes, of course. But I have a question. At the risk of embarrassing you, I found a picture. And so for the benefit of the audience and the camera here, here's a picture of 17, I don't know, maybe a little. I mean, you're ageless, obviously.
Yeah,
ageless, but such a smooth face. And so could you tell us, surprise question, I did not warn Nico about this.
Yeah.
Surprise question. History, what's going on here?
Yeah, so when I lived back in Italy, I used to play in a small band. Among 5 people, I was second guitar, but the worst guitar player of the group. It was just people were better playing drums and bass than me. So yeah, I ended up being second guitar. But yeah, it was fun.
Fun. Very good. Maybe we'll find you a band. Volunteers, band?
And a left-handed guitarist.
That is, yeah, that's an electric. Very, very nice skinny neck there. Anyway, sorry for the interruption. Let's talk about black holes.
Okay, well, yeah, thank you. Hi, everyone. So I'm Nico. I've been working here as a postdoc since October. But what I'm going to talk to you about is what I did during the 4 years of my PhD in the Netherlands. The title of the talk is On a Quest to Discover Where Stellar Mass Black Holes Emerge, Testing the AGN Binary Formation Channel with Spatial Correlation Analysis. So we're going to talk about black holes, and we're going to talk about statistics. I hope you're interested in either of these 2 topics. And so I also know that the audience is very broad in expertise, so physicists, astronomers, some people that are somewhere in between, and some people are, and also very broad in level of knowledge. Of course, I'm referring to the fact that students have just studied this stuff, at least part of it, so they are still fresh, they remember what I'm talking about. Professors, I don't know, maybe not so much. So this is just to say that if you have any questions, please feel free to interrupt me. And also during the talk, I will be way more than happy to answer all of these. And then in the last part of the talk, I will also present you briefly what I've been working on since I've been here. So yeah, I think we can start. So I said statistics and black holes. Let's start from black holes, if I can go on with my slide. Yes. Oh, too much. So there are several types of black holes. There are stellar mass black holes that we have over there, between 5 and 100 solar masses that spawn after the death of a very massive star. Then we have supermassive black holes, more than 1 million solar masses, easily to the billions. And they are at the center of, I would say, all of the galaxies. And in between, we have the very imaginative name of the intermediate mass black holes. So we have seen maybe some, but not in a consistent way. So I try to formulate the 3 main questions, I would say, that from the astrophysical and not physical point of view, we have about these 3 types of black holes. So how do they form? Still not very sure how supermassive black hole not really get where they are, but how do they form in cosmic history? Where are the intermediate mass black holes? And where do stellar mass black holes merge? So the rest of the talk will be about this 3rd question that appeared. Because as far as stellar mass black holes are concerned, we have measured gravitational waves coming from the mergers of these objects. So we have 2 black holes that orbit around each other, And if they get close enough in order to emit gravitational waves in an efficient way, then their orbit shrinks up until the moment in which they merge. And these gravitational waves, I would see them as sound waves propagating through the universe, made of universe, basically, because they are ripples in space-time itself, and they propagate until they reach Earth, where they've been detected since 2015, so we are close to the 10 years anniversary, by mainly 3 interferometers. So 2 LIGO interferometers in the US, one is quite closer to here in Washington, and one in Pisa, Virgo, the interferometer. So I lived relatively close to 2 of them, never been, so I will try to do better in future. So these interferometers have observing runs that you see here, O1, O2, O3, O4, and O5. We are now during O4, as you can see, which has actually been postponed, I learned last week, until like October 2025. Yeah. So it's going on, but the end of O4 has been postponed until the end of the year, more or less, which is great news. And yeah, then there will be a 5th run, O5, and then we still not super clear. So I said, yeah. Yes, yeah, absolutely. Okay. Okay. How do I get my cursor there? Second. This is super hard. Thank you. Okay. Yeah, so we have detected binary black holes or binary compact objects merging. So here you see them in chronological order on the x-axis and solar masses on the y-axis of the mergers that we have detected. So as you can see, so every blue dot is a black hole, every orange dot is a neutron star. And yeah, so we have seen 90 confident mergers. We have heard, sorry, 90 confident mergers, and most of them during O3. Now the O4 ones that are still getting detected yet have to be analyzed. So they will be confident, some of them in the future, but not for the moment. So most of them during O3 due to just like better sensitivity of the detectors. And yeah, so we have detected many, I would say 90 for gravitational wave astronomy, 90 is a lot. But we still don't know how these binary form. So we know there are stellar mass black holes. We know that at some point, 2 of them discover that they like each other very much. They start dancing around each other. They start dancing closer and closer and closer until they merge. But we don't know where. We don't know in what environment, okay? And this is the core question. So there are 2 options mainly. So option 1, the isolated binary formation channel. You have an isolated stellar binary system, 2 very massive stars. Both of them go supernova, first one and then the other. And if the binary is not disrupted by these 2 explosions, and you have a binary black hole that remain tight enough, then yeah, you can have a gravitational wave event from this kind of scenario. Option 2, we don't start with 2 stars. We start with a very dense dynamical environment. What do I mean by dense dynamical environment? An environment in which dynamical gravitational interactions between objects are very common because it's very dense, okay? So in this system, you can have black holes that are not in binaries, or maybe they are in very large binaries that cannot emit gravitational waves efficiently. And then due to these gravitational interactions with other objects in the environment, they get closer and closer and closer until they are tight enough to emit gravitational waves in an efficient way and then merge. What's the true underlying formation channel? We don't know. Is there a main one? We don't know. So just in case, let's add a third scenario. So the third scenario, which is option 2A, is the focus of basically this talk. So I say 2A because we are still in a dense dynamical environment. But in this case, the dense dynamical environment is the disk of an AGN. Now, I don't know how many of you don't know what an AGN is, but just in case, we have a supermassive black hole at the center of a galaxy that is surrounded by a gaseous disk. And this disk, the material of this disk, this gas, falls onto the black hole, accreting the black hole, and basically the gravitational energy of the gas gets translated into luminosity. And this central engine, very small central engine compared to the host galaxy, outshines entirely the host galaxy. So picture this disk of gas and picture a lot of black holes inside of it. Also in this case, these black holes, stellar mass black holes, they are a lot, and therefore they can meet and merge, in this case, helped by the gas that the disk consists of. So a lot of people think that this formation scenario should be or could be responsible for a lot of the gravitational wave detections that we have had. The question is, why cannot we say, why can't we give an answer to this question? Why is it so open still? And the literature is crazy. Well, this is the reason. Also, it's like also the background depicts these localization volumes. You will hear the word localization volumes a lot during this talk. But basically, as I said, gravitational waves are like sound. Okay, so when I explain this in outreach talks, I usually have people close. I won't ask you to do it, but I have people closing their eyes, and I've had asked to one of these people to clap their hand. And the thing is that if you close your eyes, you cannot really tell which person clapped their hand. You can if you're very close to this person, but the further you are, the bigger your uncertainty becomes on whoever clapped their hand. And it's the same here. It's the same here. We hear gravitational waves from somewhere in the universe. The further they are, the more uncertain we are about where they came from. And this is just to say, so this banana shape is a 90%, the bigger contour, credibility level, localization volume, area in this case, meaning that we are 90% sure that the gravitational wave event has happened somewhere in there. Now, this is a cumulative distribution function of the sizes of this 90% localization volume, credibility level localization volume. Maybe to physicists, this doesn't say much, but these are big volumes, okay? So the median, so if you take 0.5, you go until you get the histogram, it's 10 to the 8.5 megaparsec cubes. These are big volumes in the universe. These volumes can easily contain thousands and thousands and thousands of galaxies. So how can you tell which one was the responsible for the gravitational wave event, where the two black holes merged? Just to give you a couple of examples, if you take rare, so say you choose your favorite type of galaxies, this type of galaxy is fairly rare. So you have one galaxy every 10 to the 7 megaparsec cube. In the 85% of the cases, you will still have one of these rare galaxies inside the typical gravitational wave localization volume by chance, even if there is no causal connection between the two things. If you go 2 orders of magnitude rarer, so you have one of these favorite host environments, favorite galaxies, every 10 to the 9 megaparsec cube, still in 40% of the cases, you have one at least of them inside of your localization volume, okay? So these are the quantities that we're talking about. It's very rare to find the host galaxy of the gravitational wave event. How do we? What do we do in order to understand the physical origin of gravitational waves? of stellar mass black holes? I think there are three ways. First, you are lucky enough that your gravitational wave event, the merger, also produces light. This has happened once for binary neutron stars. Binary black holes are not expected to produce any light. We will go back to this. Second option, you pick whatever formation scenario you prefer, AGN disk, binary stars, nuclear star cluster, whatever you want, and you infer, you model how a binary coming from that formation scenario should look like, what masses should be involved, what spins should be involved, the eccentricity. And then you go check if there are any binaries in your data that kind of look like that. Third way, you take localization volumes of gravitational waves, here in blue, and you cross-match multiple of them with a catalog of your potential, of your favorite potential host environments. And the rest of my talk will be on this, because this is my expertise field. So what have we learned so far? We have 90 confident detection of gravitational wave events. We don't know how these binaries are formed, and we can use spatial correlation analysis in order to try to understand it, to answer this question. So, part two, I will talk about this work that I've done with my two advisors. I don't know if I named that, Elena Rossi and Sjoerd van Belzen in Leiden. So yeah, let's try to do it. Now, don't be scared from the next slide. I hope it's way easier than it looks. Not, well, okay, whatever. So the question we're trying to answer is, what is the fractional contribution of the AGN formation channel to the total merger rate? Meaning, how many of the 90 that we have detected came and have merged inside the gaseous disk of an AGN? This is our data. Gravitational wave localization volume with a size that we will call V90, and AGN in the universe with a density that we call little n AGN. And we build a likelihood function. Now, again, don't be scared. How I would like you to see this likelihood function is this. You have the likelihood is only a function of FAGN, which is fraction of the 90 detected events that come from an AGN. And you have that function SI that you see over there, that it gets bigger if for the ith gravitational wave event, we think that it might, like spatial correlation thinks that it might come from an AGN. BI, the opposite. If the ith gravitational wave event is unlikely, if you look at spatial correlation, to come from an AGN, then BI gets bigger. So how I would like you to see this likelihood function is basically a tug of war between these two scenarios, coming from AGN, not coming from AGN. And if we plot the likelihood of the ith gravitational wave event as a function of FAGN, you have two cases. SI is bigger than BI, then the likelihood is maximized at 1. So we think that gravitational wave event, that only the ith gravitational wave event come from an AGN. Option 2, SI is smaller than BI, therefore the likelihood is maximized at 0. Therefore, we think that that specific gravitational wave event doesn't come from an AGN. You smack all the likelihoods, all the ith likelihoods together, and you get a likelihood for the overall population of the detected mergers. This is the moment for questions. Everything will rely on this slide from now on, more or less. Okay. If they arise to the surface, let me know. So yeah, okay. Also not going into the details, but so what do we take into account when doing this analysis? Well, we take into account that if you build your AGN catalog, all sky, you won't have all the AGN in the universe in your catalog. So your catalog will be incomplete. We take that into account. Then we take into account where in the banana that I showed you earlier, every AGN is, if any. we maximized our likelihood, and we applied it to real data, observed data. Yes?
See that you're using the subscript I for CI as well. So is the completeness of the AGN dependent on the GW event we are looking at?
Yes, because can I come to your question in like 3 slides? Yeah, but yeah, thank you very much. So yeah, observe data. So we have to build a catalog, okay? So the red, do you see the green dots? Okay. The green dots are 242 for the spectroscopically identified AGN within redshift 0.3. Now I go back for to speak for everyone. These are very bright AGN, more than 10 to the 46 Earths per second. These are very bright guys. If we go a little bit down in luminosity, then we have more objects. These are 10 to the 45.5 or more Earths per second AGN. If we go even more down in luminosity, then we have more AGN. And also we can see that our catalog is not homogeneous, right? You see there's a U shape that is empty. That is the Milky Way. We cannot see much beyond the Milky Way. And you see there's a patch here and more or less one that is on the side. That is the SDSS footprint, which is this very cool survey that we have for AGN. So we have a lot of stuff there, more than anywhere else in the sky. And this comes to your question. So depending on where the banana of the ith gravitational wave is, we have a different value of completeness. Because if your localization volume is entirely in the SDSS footprint, that's great. If it's in, so very high completeness. If it's in the Milky Way plane, I'm very sorry for you. You will have a very low completeness. I mean, I was very sorry for myself. So, so what we have to do is to take these dots and cross-match them with gravitational wave localization areas, volumes, these ones. So these are the sky maps of the 30 gravitational wave localization of the the localization areas of the 30 gravitational wave events that were in the same redshift range of the AGN that we have. Okay, so we have the data, we let our likelihood do its work, and we get our results, which are these. So on the x-axis, you have FAGN, which is again the fraction. So how many of the 90 were originated in an AGN? On the y-axis, you have the luminosity of the AGN that you're looking at. Okay, so how bright are the AGN that you are taking into consideration? So again, are you taking into consideration the green ones, the red and the green ones, or the blue, the red and the green ones? That's basically it. So how to read this plot? Red is 90, what we can reject with 90%. Blue is what we can reject with 95% credibility. So how to read it? Let's go, sorry. So if we take the AGN brighter than 45.5 Earths per second, 10 to the, then we see that we are 95% sure, blue, that no more than we go down than 49% of the gravitational wave event come from AGN that bright. Is it clear? If we go rarer, if we go to more luminous AGN, then we are 17, more or less, I think, % sure that, no, sorry, we are 95% sure that not more than the 17% of the detected gravitational waves come from an AGN, okay? And as you can see, the more luminous the AGN that we consider, the tighter the constraints that we can put are. This is fairly easy to see why. So this is the scenario that I pictured before. If we consider more AGN, yeah, so less luminous AGN, then this is the scenario that you get. And it's very hard, you know, to say, okay, because one galaxy has generated that gravitational wave. So if you have more galaxies in your localization volume, then it's much harder to distinguish what is signal and what is noise. On the other end, if you consider very rare AGN, then it's basically a yes or no question. Is there an AGN in your localization volume? Yes, awesome. Maybe that's the culprit. Is there no AGN in your localization volume? Yeah, there's none. So I don't think your gravitational wave event has come from an AGN. So our constraints really depend on the number density of the AGN that you consider. So what is the fraction? And yeah, these results are the first observational constraints on the origin of stellar mass black hole that we have seen, that we have heard merging. So the question that we asked some time ago was, what is the fraction of the contribution of the AGN channel? What is the fractional contribution of the AGN channel to the total merger rate? The answer is, depends on AGN luminosity, but we are 95% sure that less than half of the events have come from AGN brighter than 10 to the 5, 45.5 ergs per second. Next part is going to be, yeah, please.
If we're just random, what would you expect?
If they were randomly distributed,
We're just distributed among all AGN. Right. So this one's not this one's.
well, that's what we do expect. And because, okay, depends who you ask, but people, I personally think that the efficiency in generating these objects, these binaries, does not depend on the luminosity.
So that's just a selection.
Absolutely. Yeah, absolutely. Yes. We can talk so much more about this because there are some luminosities for which they say that it's very likely that they don't produce any gravitational wave event, but yeah, it's a long topic. But in this case, just selection. Yeah. Yeah. So third part of this talk out of 5, very quick one. So we have seen that we can do something. What about putting tighter constraints with respect to the ones that I just showed you? And we all know to put tighter constraints, you need better data. Do we have better data? So that's the question that I was asking. So can we put any tighter constraint? So let's talk about what data we have. So these on the y-axis, you see luminosity distance from Earth of the detected gravitational wave events, and every marker is a gravitational wave event in chronological order. So in the previous work, I have used only the ones in this little area because I was restricting to close redshift. But in June 2024, we had these objects, okay, these gravitational wave events. Now, caveat, the purple ones are from 04. So it's quite likely that they are binary black holes merging, but yet not confident. So I try to be very conservative, but still some of these points could not make it to the final catalog. So yeah, my goal was using all of these data because this is amazing. This is 159 gravitational wave mergers. Yeah, binary black hole mergers. But in order to cross-match with this type of, with going further in distance, you need a very good AGN catalog. Luckily, I was contacted by Kate Story-Fisher that had put together, in my opinion, a very nice AGN catalog called Quaia, because it's the quasars from Gaia. And so as you can see, maybe it's very complete. Like the green is very uniform apart from, of course, the galactic plane, okay? So this is a very good catalog, or at least it looks like. Then we have to cross-match it with the gravitational wave events that you see. In this case, I plotted luminosity distance, so just as before, as a function of size of the localization volume. And as you can see, the further the gravitational wave event is, the bigger the uncertainty becomes in the localization, because it's just, yeah, it doesn't sound as loud. Okay, so very quickly on this, we estimated the completeness of Quaia as a function of redshift and as a function of luminosity of the AGN. You can see here, so these are number of AGN as a function of redshift. So how many AGN you expect in specific redshift bins. Different colors are different luminosities. Dashed line is what you expect from quasar luminosity functions. Blue markers, round markers are how many we have in Quaia. Basically, the fact that the markers, at least for the blue, green, and red line, follow quite nicely this trend which is completely uncorrelated from the point of view, like markers come from some data, line comes from some other data. They are not dependent at all. This means that Qualia is very good for our purpose. So again, we ran the same likelihood analysis, and we ended up with these constraints. Now the dashed line contains the region of the parameter space that I rejected in the previous work, right? With worse data, like less data. And so as you can see, we went a little bit more down in luminosity also. So we consider also AGN brighter than 10 to the 44.4 ergs per second. So we consider a larger population of AGN, and still we are able to put very tight constraints. So the question was, can we put better constraints with better data? Yes. And we gain a lot of constraining power, and we can say that we are 90 or 95, not good, it's not written. I think 90, oh wait, 90, 95. Well, either 90 or 95. We are fairly sure that not more than 20 or 10%, depend what luminosity you consider, 20 for the dimmest ones, 10 for more or less all the others. Not more than 10% of the gravitational wave events that we have measured come from an AGN. And these constraints start to be very, very tight, in my opinion. Part 4, slightly unrelated, but not so much. In 2023, there was a paper, there was a paper that suggested that, on the contrary with respect to what I told you earlier, there were some gravitational wave event, binary black holes, that produced light. I will tell you in a second how. This light was flares in AGN. So we had an AGN working as normal as an AGN can be, which is not at all. And you can see a flare on top of the normal trend of the luminosity of this AGN. So the pink dots are the position that these were measured by the Zwicky Transient Facility. Pink dots are where in the sky these events, these AGN flares were. Blue is the cumulative distribution of the co-moving distance, but so how far they were from Earth. And this is important. This is, you have modified Julian days, so time on the x-axis. The dashed vertical lines are when these flares peaked, when these flares were. Green boxes are when was the third gravitational, the third observing run of the LIGO and Virgo interferometers. And so these flares were searched and found during this time, the third observing run of the gravitational wave of the LIGO and Virgo interferometers. And there were some that were measured during this time. Now, okay, what is happening according to modelists? So you have a binary of stellar mass black holes that is dancing in the accretion disk of a supermassive black hole. They merge, and the remnant of this merger gets a recoil kick, this is standard, from the site of the merger. And if the remnant escapes the accretion disk, then you might have the drag that this recoiled black hole was dragging along that can show up as a flare in the AGN. So this is the idea. Again, same stuff, basically same stuff. The only difference, so we ran basically the same thing as before, using AGN flares as potential electromagnetic counterparts of the binary black holes. A lot of difficult words in this sentence. But in this case, there's a difference. In order to be a match, it didn't have to be only a spatial match, but also a time match. Okay, so the time difference between when the gravitational wave event happened and when the flare happened, had to allow a causal connection between the two events. Okay, these are the results. Just look at the blue line. We ran our analysis and we found this is the probability, the posterior probability of F flare, which is basically FAGN of before. So how many of the gravitational wave events are causally connected to these flares? And we see these posterior peaks at 0, and this is the 90%, the vertical line, 90% credibility level. At 90% credibility level, less than 15% of the detected gravitational wave event produced a flare. One claim was that, with the data, 12 matches were found between, so spatial and temporal match were found. The claim was that these were too many matches to be only chance, only random. Not so much, because what we did was simulating some Monte Carloing random case. So we picked random gravitational wave events, random AGN flares distributed in a way that made sense in order to be detected by Zwicky and so on and so forth. And the bluish, the light blue distribution is the distribution of how many matches we had in each of these Monte Carlo realizations of the background scenario. And as you can see, 12, which is the vertical dashed line, is well within this distribution. So the fact that you have 12 matches doesn't mean that you have a causal connection. It's very well within the distribution of just random. Same. Sorry? So these are, so the flares were, so in this case, you have 20 flares that you cross match with, not 90 because it was only 03. Sorry?
Up to the end of 03, we had 90.
Yeah, but only 03, they were like 80, something like that, yeah. And these 12 are one-to-one matches, meaning that if an AGN matches, if a flare matches with 2 gravitational wave events, that's 2 out of these 12. Same vice versa. If 2 gravitational wave events match with 1 flare, that's also 2. Another argument was brought up in the claim paper, and it was that the gravitational wave event matching were the ones among the ones with the heaviest masses, okay, with the heaviest black holes in them. And if you model your AGN disk and so on and so forth, you find out that you predict heavy black holes, heavy binaries to form in AGN disk. So the claim was that, awesome, we expect heavy black holes to merge in AGN disks, and the ones that we see matching with our flares are all heavy. Yes, that's true, but this plot shows size of the uncertainty of the localization volume as a function of mass of the binary. And as you can see, so the pink markers are the AGN flares, sorry, the gravitational wave events that match with a flare, with at least one flare. And as you can see, they are fairly, so the dashed lines are the medians. So they are heavy binaries, yes, but they are also associated with the biggest localization volume, meaning that it's easier for them to have a match, just due to, space. So I won't bother you with this, but also in this case, we ran Monte Carlo simulation of random scenario, checking the masses of the events that ended up matching in our Monte Carlo simulations. And also in this case, the quantities that were observed, still very well explained by random case. So the question that we asked was, 20 unusual AGN flaring activities have been identified as potential electromagnetic counterparts of gravitational wave events. Is there a cause-effect relation? Very polite answer. Currently available data suggests that the spatial and temporal matches are compatible with the hypothesis of no cause-effect relation. Okay, end of what I did during my PhD. Now, what the hell am I doing in here? So I basically doing not so different stuff, but I'm working on seeing what we can hear, meaning that we have at the center of each galaxy a supermassive black hole. When two galaxies merge, the question is, do also the supermassive black holes at some point meet and merge after the galaxies merge? Or do they stall somewhere? What's going on? And so the question that I'm trying to answer is, say that we have a detection. Will we have catalogs of galaxies, of potential galaxies in which these mergers of, in this case, supermassive black holes happen? Let me explain a little better. So for the first part of this talk, we were here. Here. So ground-based experiments seeing merging stellar mass black holes, okay? We are talking 10 to 1,000 hertz, more or less. Now let's move on 7 orders of magnitude in mass, or let's move down 10 orders of magnitude in frequency, and we have merging supermassive black holes, okay? So these objects are not seen in the moment of merger, but are heard, while they are still orbiting, okay, with a frequency of the order of the nanohertz. How do we hear them? Yeah, this is what I was saying earlier. Galaxies that get closer and closer, galaxies that merge, and the question is, do also the black holes merge? How do we hear them? Now, in the universe, we have pulsars. Pulsars are neutron stars, fastly rotating, that they can emit, a cone of light. If during the rotation of the pulsar, of the neutron star, the cone of light intercepts the line of sight with Earth, then we have this lighthouse effect, which is incredibly precise. Pulsars are the best clocks of the universe. So you can model very well when the pulse of the pulsar should arrive at Earth. Meaning that if you can model this and you can check whether there are discrepancies between the time of arrival of the pulse and the time in which you think the pulse should arrive, this could be, if there is a difference, this could be caused by gravitational waves that are crossing the space-time, that are deforming the space-time between us and the pulsar. Okay, so far, very likely, even though it's still open to debate, we have heard a gravitational wave through pulsars, pulsar timing arrays, this is how it's called, the whole infrastructure. We have heard a gravitational wave background, meaning that this background that we have heard, this noise that we have heard, might be millions, I guess, like a lot of supermassive black hole binaries that are, dancing at very low frequencies, but we are still hearing the crowd, okay, without being able to select one voice of the crowd, okay? So we are hearing the orchestra. We are hearing all of these binaries playing together. We are not being able to hear one of them. But we do expect that the first soloist will be heard in the next 5 to 10 years. In 5 to 10 years, we expect to have the detection of gravitational waves coming from one binary, plus all the background of the others. So the loudest one. What then? So we have this. What then? We estimate how bright should be. So this is what I'm doing here. So we estimate how bright the galaxy in which this orbiting is going on. And we construct catalogs of binaries with these characteristics. And then you have your localization area in the sky. You have the ad hoc catalog that we have created. Now it's time to check each of these galaxies to see, or at least the most promising ones, to find a smoking gun detection in electromagnetic radiations or light detection that can tell us, okay, there's a binary there. And the goal is to implement all of these things into the pipeline of all the pulsar timing arrays. Because, and this is something that I should have said 45 minutes ago, if you have a multi-messenger detection, so gravitational waves and light, it's, in my opinion, the best playground, among top 5 playground in science. Because you can do so much from the astrophysical point of view, from the cosmological point of view, from the physical point of view, so difference in the speed of light with respect to speed of gravity and so on and so forth. It's got, yeah, I think that if we have a multi-messenger detection of a supermassive black hole binary, that would be amazing. Yeah, so very quickly, this is basically my last slide. Yeah, let's not bother about that. Well, later. So what I'm doing is constructing this pipeline, basically, in which you take masses, distances, mass ratio, so how much one of the two black holes is more massive with respect to the one. And you take these binary parameters and you translate them into distributions of magnitudes of the host galaxy. Okay, so then we have gravitational wave data on one end, electromagnetic, so light data from on the other end. Let's see if we can find the culprit. And yeah, so these plots are very preliminary plot for what I've done so far. And we have basically distance of the binary as a function of so yeah, and total mass on the other on the x-axis, and the blue lines are the borders at which we will hear these binary. Basically, how far it has to be and how massive it has to be, or let's say how close it has to be and how massive it has to be for us to be able to hear it in the next. This is 5 years. While so whatever is in gray is something we can hear, while the lines are for so how deep we are with electromagnetic surveys. So surveys of yeah, light coming from galaxies in the sky. And the fact that all the lines are basically, all the colored lines are always above the black ones, means that we are fairly sure that whatever we will hear in gravitational wave, we will also see in light. The goal will be then choosing the right one. Okay, I will leave you to my conclusions. The astronomers have already seen these conclusions. They are not the typical conclusions. So when you defend your thesis in the Netherlands, you are asked to state 12 at most sentences that are called propositions. 4 of them have to be on your thesis. 4 of them have to be on science in general, and 4 of them have to be on whatever you want. But you have to be ready to defend these sentences during your PhD defense from a scientific point of view, like through scientific argument. So I will leave you with these conclusions. I have put like in a box the ones that are relative to the topic. And yeah, thank you very much. I'm ready for any question that you have.
You just briefly say what an unusual flare is.
So, light curves of AGN are messy. So if you measure the luminosity of an AGN as a function of the time, it's very, very difficult to extract any specific signature. But some of them might be supernovae happening in the galaxy, in the host galaxy. Tidal disruption events happening over there. So tidal disruption event is when you have a star that gets eaten by a black hole. And a regular AGN variability, regular as in we don't know what is caused from by, but it's there. So these 20 flares were selected as being not compatible with supernovae, tidal disruption events, and AGN variability. So if they were what was left.
Just in case you remember, for the GW events which were coincident with the AGN flares,
Yeah.
did the authors make any comments about the eccentricity evolution of those GW?
No, because in LIGO, when a binary reaches the LIGO waveband, so gravitational waves, so you have binaries that orbit around each other. They emit energy in the form of gravitational waves. This emission is very efficient in circularizing orbits. So by the time they enter LIGO, they are usually very circular. So by the time they are starting to be heard by LIGO, or Virgo, they are very circular. There have been searches for eccentricities in the data, but I don't think any confident conclusion was made about it. So yeah, no eccentricity information. Assumption, they are all circular.
So you said about 20 Indian players, but been explained by traditional.
Yeah.
So have people followed up those 20? Because we at least know the time and scale of mission. Follow up meaning by looking at archived gravitational wave data.
Not as far as I know. It's also true that a lot of people think that, I don't know, like I'm not a modelist of AGN light curves, but people think that some of them, the AGN regular variability option was discarded a little bit too harshly, let's say. So we don't know what these AGN flares were, I guess. But, or maybe some of them were counterparts of gravitational wave events, but I don't know. And so, yeah, I don't know. What did I want to say?
So I didn't find any association.
Yeah, no, exactly. And we
Groups here who can actually do that.
yeah. If you're into light curves, have fun.
So if within the next 5 or 10 years you detect here, as you say, one of these supermassive mergers, macro mergers, how much time do you then have to go and look for an electromagnetic signal? Are these events that just go on forever, unlike the solar mass black hole?
Correct. Yes. So the thing is, we don't. So PTAs, pulsar timing arrays, don't hear the mergers. They hear the binaries when they are still orbiting around each other at with timescales of 10 to the 8 years. So yeah, this like one period of these orbits is 10 to the 8 years. So yes, you can be very chill in looking for electromagnetic counterparts. Yeah.
Is 10 to the 8
Seconds.
Yeah, yes.
10 to the 8 seconds. Yes.
Yeah.
Sorry. Yeah. Yeah. I got misled by the yeah. Because it's 1 over 10 to the 8, 10 to the minus 8 hertz. Yeah. Yeah. Thank you.
Anything else? Maybe check Zoom real quick.
I don't see anything.
Let's thank Niccoló.